Okay, welcome back to Homework 2 of Material Energy Balances class, where today we'll be talking a little bit about non-ideal gases. So, let's think about how we can characterize a non-ideal gas, and what a non-ideal gas is. So, what conditions constitutes non-ideal? Well, conditions where the molecules actually are so close to each other that they start seeing each other, and where the temperature is so low. In other words, the kinetic energy of the molecules are so low and the velocity is so low that when the molecules pass each other, they experience a non-negligible force between each other. And we can explain that with just the ideal gas law, and we can come to what's called the van der Waals equation of state. So, ideal gas law is PV equals RT, where N is equal to 1. We assume that it's 1 mole of gas, so we are not so much concerned about how much the moles change. Bring V to the other side, P equals RT over V. Okay, and let's start making corrections that van der Waals did. And the first correction that van der Waals implemented is that the molecules are not in fact point particles and do take up a certain amount of volume, and we call that volume B. Okay? And second, the force that the molecules exert on each other is not non-negligible, and it is characterized by A over V squared. And the reason why, let's pull out my laser, this term is subtracted is because it is a force that works against the observed pressure. The higher that the force exerted between molecules is, the lower the observed pressure is. So this is the van der Waals equation of state. But how do we find A and B? Well, the really smart thing is it's not completely through experimentally determined data where we just go through and test every value of P, T, or V. Or one important caveat to mention now, that V is not volume. V is specific volume. In other words, the inverse of density, where 1 mole of stuff or 1 kilogram of stuff takes up a certain amount of volume. So gas would have a very high specific volume because it has relatively low moles, but takes up a lot of space. And liquid has a fairly low specific volume or a fairly high density, where a single set amount of space has a lot of mass, a lot of matter in that area. Anyway, the way we can determine what A and B is to look at the different isotherms of the PV diagram. And the important thing to mention is that this line right here is the critical isotherm, or the critical temperature where critical pressure would be. And what do you notice about this region right here, the critical point? Remember that the critical point is the pressure and temperature where the properties of vapor and liquid become non-distinguishable, and it's a set point for any matter. It is special for any form of any compound, I should say, unique for any compound. Okay, this point doesn't change. But what do you notice? Think back to calculus 1, okay? What do you notice about this line, and what's special about the critical point? Well, for starters, it's a maximum, right? So what does that tell you about the first derivative? It tells you that the first derivative, dx, or we should say dv, dp dv is equal to 0. Oh, what's next? It's also an inflection point where over here it's concave up, or rather over here it's concave down, and over here it's concave up. Well, we can then say that the second derivative of this function is also equal to 0. Well, we have a function that we can partially derive with respect to volume, but it's important to mention that when you derive this, the terms of the equation actually change, okay? Because you're partially deriving pressure with respect to volume, assuming that the temperature is equal to the critical temperature and the volume is equal to the critical volume. Okay, what's the first derivative? Well, it's easy. Okay, minus RT over V minus B squared. Okay? Now, this isn't a calculus class, so I won't go into detail how the what derivative rules we're using, but we're continuing. This time it's plus, because negative times negative, 2a over v cubed. And we say that this is equal to 0. Okay? Next, we partially derive again, so this is now the second derivative of the PV function, the isotherm at critical temperature, assuming that the temperature is equal to the critical temperature and the volume is equal to the critical volume. This is equal to positive, this time because negative times negative, RT over V minus B, 2. Don't forget to bring up the constant. Negative, not negative, cubed. Back to negative. 6a over V to the 4th. And equals 0. Okay? Now, because that this expression is equal to 0, we can set this expression equal to that expression. So, let's do that. We're changing color. We can say that RT over V minus B squared, quantity squared, is equal to 2a over V cubed. And we can say that 2RT over V minus B quantity cubed is equal to 6a over V to the 4th. Now, I'm sure you've noticed, but I did a little bit of an oopsie here, and I noticed it as I'm writing it down. Remember how I mentioned that the terms of the equation change when you derive it, where T is now equal, it's not any T, it's the critical temperature, and V is not any volume, it is this critical volume, okay? So let's write in those terms really quick. Critical temperature, critical volume, critical temperature, critical volume, critical volume. All right, let's look at our equations now. What do we have? We have a system of 2 equations and 2 unknowns. And every other term except for A and B, we know, because we can get it from the CHE tools package. Critical temperature, critical volume. R is the universal gas constant, we always know that. And the only unknowns are A and B. There we go. We now have a system of 2 equations and 2 unknowns that we can solve for A and B. Okay, so at this point we have a system of equations with 2 unknowns to solve, right? And the way we go about that is we take the reciprocal of this equation and then multiply it by that to cancel out some terms. So let's go ahead and do that. But first, we'll focus on this side of the equation. So what that is going to look like is, we'll change the color blue here. So it's going to be VC minus B cubed over 2RTC times RTC over VC minus B squared, right? So let's see, some terms cancel out. This is gone, that's gone, the cube is gone, and that entire term is gone. So we get VC minus B over, over 2. And we'll do the same thing for this side of the equation. Okay, so we get VC to the 4th over 6a equals, multiplied by 2a over VC cubed. What cancels? This entire term, that exponent, the A, and this turns into 3. So on the right side of the equation, we now have VC, well, over 3, right? Seems about right to me. Now what we can do is multiply the denominator to each side of the equation. We now have 3VC minus 3B equals 2VC. Okay, now let's isolate B. 3B, well, negative 3B equals, oops, I did not want to bring that up. Minus VC B equals VC over 3. There we have it. We now have our B term. Let's highlight that. Okay. Now, next step, we'll plug that right back into this equation right here and see what happens. Okay? So, let's make this green. RTC over VC minus VC over 3 squared equals 2A over VC cubed. Okay? This turns into RTC over 2 over 3 VC squared. Okay, the 2 over 3, we'll just square the 2 over 3. That's too big of an eraser. Becomes 4 over 9 equals 2A over VC cubed. Actually, tell you what, we'll bring the 4 over 9 out of the denominator by taking the reciprocal, and that becomes 9 over 4. Alright. Now, we bring that constant 2 over to the same side. We want to try and isolate A here, so 9 over 8 and the VC cancels. Just that exponent, and then bring the VC to the top. We now have 9 over 8 RTC VC equals A. There we go. We now have the expression for A and B for the van der Waals equation of state. Let's highlight that to point it out. And it's just that easy. No messing around with experimental values. All we really need to know is the critical temperature, the critical volume, and the universal gas constant. Alright, now at this point we know A and we know B. We can move on and calculate the compressibility factor for the van der Waals equation. And what that kind of tells us is the compressibility factor for any compound. We'll go right into that. But first, what is the compressibility factor? Well, most, if not all, chemical engineering classes will tell you that the compressibility factor is called Z. And it is equal to PV over RT. Looks familiar, right? And for an ideal gas, Z is going to always equal 1. But for a lot of chemical engineering processes, we're not going to be at ideal conditions. So Z is going to be different from 1. Okay? So, in order to find the compressibility factor, we can take our van der Waals equation of state. excuse me. Where P is equal to RT over V minus B minus A over V squared. And we're going to say that, okay, we are at critical temperature, critical pressure, and critical volume. So, and knowing that, we can also plug in A and B. So let's do that really quick. This equation will start to look messy, but you will see soon that it mathematically cancels out. So we'll call this PC now. PC, the critical pressure, is equal to R times TC over V minus, remember, RB is VC over 3, VC over 3 minus A over, oh sorry, we plug in A, and our A is equal to 9/8 RTC VC. So we'll put the constant outside. 9/8 RTC VC all over V squared. And you can immediately see that some things are going to cancel out. Okay? So let's see. Right here, VC and this squared cancels out. This expression becomes 2 over 3 VC, right? And then we can bring that 2 over 3 up outside of the denominator by taking the reciprocal, which the equation will now look like this. PC equals 3 over 2 RTC over VC minus 9/8 RTC over VC. Look at that. We have like terms and two coefficients. We can factor out the RTC over VC. RTC over VC. And get the two constants in a common denominator, which is 8. 3 times 4 is 12 minus 9 over 8. PC equals RTC over VC times my mental math is not great, but we now have the coefficient of 3/8. Look at that. We have, let's get the laser pointer, we have all the terms. That is the expression for compressibility factor. Let's get it into that form. Okay, so now PC times VC over RTC. Look at that. That is now the same form as the expression for compressibility factor, and it's equal to 3/8. What's incredible about this is van der Waals is essentially saying that the compressibility factor for any gas, any compound in the gaseous form, is going to be 3/8. And we can say that because we use the van der Waals equation of state, and based on critical temperature, critical pressure, critical volume, we calculated expressions for A and B, plugged it back in, and we come to the same expression that describes compressibility factor. And it's always going to be 3/8 because the critical volume, critical temperature, and critical pressure are one set point for any given compound.